Today we're doing 8.5, which is called products with radicals, and going to start out with geometric mean. It's a small part of the section, but usually I end up going over it in class if I don't put it in the notes. Mean should be a word that you recognize from before. Mean simply means the average. So normal, and I wouldn't write this down, but normal the way we've done the mean. So say we were to look at some people in the classroom, we're trying to figure out the average age of the people in the classroom. And we'll get people ranging from, I don't know, usually 14 to 18 in the class. But say we have a 16 and 17-year-old. If we're trying to calculate the mean, we add them, we divide by the number that there are, and we get 16.5. So that's going to work. The way that geometric mean is usually used is if you have one person that is an outlier, has an age that's radically different from the rest of the group, or a number that's very different. So say we're going to throw me in there. Right now I'm 39, and now we'd have to divide by 3. Well, if we did that, you come up with an average age of 24, which totally doesn't work. You know, most of the class, and I probably should throw in some more people, but one number that's way bigger is going to radically skew your results when you're doing mean the way that we've done in the past. So this geometric mean looks this way. So geometric mean, I'll just write it here afterwards. So that equals, instead of adding them all up, we're going to get the product. So I'm going to leave a little space, and I'm going to say the product of the numbers. So now instead of doing 16 plus 17 plus 39, we do 16 times 17 times 39. And then instead of dividing by 3, in that case we do the cube root, but I'm going to say n, where n equals the number of, normally I probably just would say numbers, but I'm going to say elements. How many things did you take and multiply together here? Before, when I calculated mean the old way, I came up with an average of 24 for a 16-year-old, a 17-year-old, and a 39-year-old. If you do this geometric mean, you come up with 22. It's not much better, but it's at least closer. The main part of the notes, though, is going to be this here, both simplifying radicals with numbers, but also we'll do variables. And it's something that's very important that you get. So if you don't get this from the notes and in the homework, please ask questions. Please, 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 let's go over it in class. There's a couple ways you can do it. One way is the way I learned in high school, where you take and you try to pull out small numbers. So say I'm given the square root of 50. You try to pull out small numbers, and that's not a real good example. Maybe the 252 would work better. The problem I had with that is if you're taking small numbers out, I wasn't always sure when I was done. So sometimes I'd turn in my quiz, I think I'd simplified the radical as much as possible, and then turns out, no, there's one more thing, you could have pulled out another 4 or another 9. So I like teaching it with these steps here, and they're fairly abbreviated. But this way you can go through and simplify the radical really just in one step and know you have the right answer. It's really kind of up to you. We had these index cards in class from chapter 7. Some people are real dependent on these. I'm torn. One side of me, I like that you kind of see what's happening, but I don't want you to need that for the rest of your life. So I'll come back to that in a little bit. But the steps are going to be this. You take your original number, so in this case it's 50 for my first example, and you cut the number in half. You might want to pause the video and quick write these down, or after I get done explaining it, pause it, quick write them down. So when you cut the 50 in half, 50 divided by 2 is 25. That's going to be your starting point. So you don't use the 25 later on in the calculations. You just know that you're going to start here at the 25. Then what you do is you go back to your original number, which is 50, and you divide it by these perfect numbers on the index card. Because we're doing a square root here, we will use the perfect squares, what all the numbers squared give us. When we're down here doing the cubed root, then we're going to take the 375, we're going to try to divide it by the 8, the 27, the 64. We're going to use some of these numbers. And the reason is when we do a square root of one of these perfect squares, it works out into a nice integer answer. when you do the cube root of one of these numbers, you get another nice natural number or integer, no decimal answer. So the original number 50 divided by perfect numbers until you don't get a decimal. Then you do you write the perfect number from the index card and the remainder, and then you simplify. So copy them down quick. It'll make a lot more sense when we do a couple examples. So what I'm trying to do is I'm trying to take this 50, I cut it in half, I get 25. Then I'm going to do 50 divided by numbers on my index card starting with 25. Well, this one works out the first time, because if I take my calculator and I do 50 divided by 25, I'm going to do that quick a second, even though I know the answer. 50 divided by 25, I get a 2. And from there, then I know that 25 times 2 gives me 50. So where this is called like products with radicals, what it's really saying, and usually I don't write this, but what's really happening is we're saying not that. We're saying square root of 50 could be written as square root of 25 times 2, because 50 divided by 25 is 2. And now when you have a radical with multiplication inside, as long as both of them aren't negative, it's legal to split them up. So we could write that as the square root of 25 times the square root of 2. So step number 1, I found that 25 is my starting point. Step 2, I do 50 divided by 25, and then I don't get a decimal, so I found the number I'm going to use. It's going to be that 25. So we just did step 3, write it as the perfect number, the square root of 25, and the remainder, square root of 2. And now we simplify. Square root of 25 is 5, and then that's times the square root of 2. If you punch in square root of 2, you get something ugly. We can't simplify that more without having it be rounded. Square root of 2 gives you an irrational number, a number that keeps going on forever. All right, those steps will work here for the 252. We're going to take and try to write it as two different radicals. So I start out with my 252, and I grab my trusty calculator. And I say 252 divided by 2, and I get 126. So what that's telling me then is any number that's bigger than 126 is going to be too big. So if I try to do 252 divided by 144, it's not going to work. It's too big to even go into it twice. 252 divided by 169, too big to even go into it twice. So then what you do is you start at the first number that's smaller than that 126, which would be 121. If you're sure something's not going to work, skip it. If there's any doubt in your mind, though, try it. So I'm going to pretend there's doubt in my mind. I'm going to do 252 divided by 121, and I get a decimal. So then I try the next number up, which is 100. So 252 divided by 100. I get another decimal. Then I do 252 divided by the next number up. So I'm kind of working my way up my list over here. So now I'm up to my 81. 252 divided by 81, 3.11111. So 252 divided by my next one, my 64. I get another decimal, 252 divided by 49. So this part here can feel a bit tedious, but the nice part is once you get the number that works, you know you have it simplified completely. So I worked all the way up until I got to this 36. And when I did 252 divided by 36, I got a 7 for an answer. So I could write it then as square root of 36 times square root of 7. Square root of 36, well, we're saying what squared gives me 36? The answer has to be a 6. So the simplified version is 6 times the square root of 7. Cube root of 375, do everything exactly the same. We'll still cut it in half. We'll still divide by 2. But then we want to use our cubed root. So we'll use our third power column, this column over here on the index card. So 375 divided by 2. And I get 187.5. Nice part for these is the numbers get smaller faster. So 187.5, my first number to try is going to be 125. And if you look at that, you'll see that it's going to work. So 375 divided by 125 is 3. So we don't need to try the 64, the 27, or the 8. We just write this as a cubed root of 125 times a cubed root of 3. Now cubed root of 125, what to the third equals 125? It's going to be 5. So this just becomes 5 times the cubed root of 3. And that would be simplified. fourth root of 12,005. So do the same exact steps. We're going to write it as 2 fourth roots though. So we'll divide that by 2, you get 6,002.5. So now we look over at our column here. So I'm a little bit short. I don't have a 9 to the 4th. That should be too big though. But 9 to the 4th is 6,561. So sure enough, that's too big. So then I'm going to start then with my 4,096. So 12,005 divided by 4096. Doesn't go into it. 2.93 yada yada yada. So 12,005 divided by my next number up in that fourth power column. So we're doing fourth roots. 2401. And I get a 5. So then I could say that this here is the fourth root of 2401, 2401. My remainder was a 5. And now what to the fourth is 2401. It's going to be a 7. So 7 times the fourth root of 5. Let's move on. Variables. Variables, they look tricky on the surface, but there's actually a trick which makes it quite nice. It's kind of easy to get. If you think back to if we did, so this stuff in green, write it, don't write it. I'm just kind of trying to prove a point. But if we have the square root of x squared, and you could say, well, that's the same as x squared to the 1/2 power, which then just equals x. And we're going to kind of talk a little bit more. That's not really the whole story, but you need to see the notes on 8.6 before you go too much further there. So when you have the square root of x squared, you could just say, well, that's x. If you have the square root of x to the third, now if we try to do that, we're going to get x to the 3/2. So you could say x to the 1.5, which I suppose then you could say x to the 1 is that. X to the 1/2 is another square root of x, which actually is the final answer. The way the book likes to look at it, though, is they say, well, that square root of x to the third, you could write that as the square root of x squared times x. Because if we combine these two together, it'd be a 1 there. So you could add your exponents together and you get an x to the third. Lost the whole thing. But going back to what we just did in the earlier section, if you have multiplication inside a radical, unless they're both negative, you could say that's the square root of x squared times the square root of x. And now doing what we did above, square root of x squared, well, that just equals x, so this becomes that. And we have this x that's still stuck inside the radical. That's kind of the theory behind it. This is the shortcut, and this will save you tons of time. What I do is I look at it this way. 2 goes into 3 how many times evenly? So if you're doing multiples of 2, you have 2, 4, 6, 8, 10. So it goes into 3 once evenly. So then we could pull out an x to the first, so we can pull out one x here. Well, then how many of those 3 x's does that get rid of? Well, that took out 2 of them, so 1 of the 3 is left inside. And I'll do this kind of both ways. The easier way, I think, is to say, well, 3 goes into 5 evenly how many times? Once. So then we could pull out an x. And then how many of those 5 are left inside once we took out that multiple of 3? 2. So it'd be x times the cubed root of x squared, because 2 are still stuck inside. If we were to go and do that same thing here, 5 goes evenly into 4 how many times? None. So inside my radical here on the right, I'm still going to have an x to the 4th. I can't pull any x's out because I'm doing multiples of 5 with a 5th root. Well, 5 goes into 7 evenly how many times? So 5, 10. So it only goes in once. So I could pull out a y to the 1st, because that's going to be how many times y goes in. That gets rid of 5 of my 7 y's. So I have a y squared inside. Then for z's, 5 goes into 12 how many times? 5, 10, 15. So 5, 10 goes in twice. So now instead of having a 2z, I have a z squared. That your exponent on the outside will always be the number of times the multiple can go in. And that takes care of 10 of my 12 z's. So I have a z squared stuck inside. Really what this is doing is it's taking this here, if you want to kind of see the math argument behind it. It's saying cubed root of x to the fifth, and I wouldn't write this, but that's the same as cubed root of x to the third times x squared, which then is the cubed root of x to the third times the cubed root of x squared. Cubed root of x to the third just gives me an x to the first. Cubed root of x squared is what's left inside. You can do that same thing, maybe I'll just do the z's over here. But you could say, well, z to the 12th, that's the same as z to the 10th and a z squared. So the fifth root of z to the 10th times the fifth root of z squared. And then this is the same as z to the 10 over 5. If you change it to an exponent, so that's a z squared, which is what we had right there. Then this here we still have stuck on the inside. So we have a z squared and the fifth root of z squared right there. So that's kind of the math argument behind it as well. The very last part is to do an example that combines those last two things together. And so we'd have cubed root of 320 x to the third, y to the fifth, z to the 13th. I really just treat this like two problems and kind of mash the answers together at the end. So I'm first just going to do the cubed root of 320. And usually as I do these problems I don't rewrite it. I just want to kind of show it. So I'm going to look at this problem first, then I'll go back and do the variables next. Now I could go back and grab my index card from a couple pages before, but I kind of want to show how do you do this if you don't have an index card. Alright, so I'm doing cubed root of 320, so I need to do my third powers. If I didn't have my index card, what I would do is, well, you could go through and you could list out, you could type in 2 to the third, 3 to the third, 4 to the third, and kind of write out the numbers in the margin. That works. Takes a little bit of extra time, but it would work. What I want to do is I want to figure out what's my biggest number that can't go into it twice. So I'm just going to kind of take a shot in the dark and say, well, 320 divided by 5 to the third. So I'm not even bothering figuring out that 5 to the third is 125. So it doesn't work. I know that because I get a decimal right there. But the other thing I found out is there is a number that could be bigger. So then I'm going to do my 320 divided by 6 to the third. Now once I have 1.48, I know that 6 to the third is too big to even go into it twice. So no point trying 7 to the third, 8 to the third, because those are going to be way too big. So the number that works, if any number works, has to be one of the numbers smaller than 5. So then I could do 320 divided by 4 to the third. And that works. So now I just need to figure out, well, what is 4 to the third? And 4 to the third is 64. So I know then that my 320 is divisible by 64, and my remainder is going to be 5. So now as I go back to my problem here, I say then my cube root of 320 has cube root of 64. And my remainder, I forgot it already, 5 was it? 5. Cube root of 5. And you really don't even need to look up that 64 unless you're trying to show your work, because really what you're just trying to find is, well, what to the third is 64? So it's going to be 4. So this cube root of 64 becomes a 4 times the cube root of 5. So I'm going to leave a little space between those two. And I have 4 times the cube root of 5. So what I did is I just simplified the left half of that problem. I got my number, I pulled out as much of that 320 as I could. Now I just need to go through and do my variables. So the space I left right there is space to write down the variables that I'm able to pull out. So now you just do what we did in that last section. 3 goes into 3 how many times? Once. So I can pull out an x to the first. When I pull out 3, how many of these 3 x's in there are left? None. Now 3 goes into 5 evenly how many times? Once. As soon as I do 3, 6. 6 is too big. So I just pulled out 3 of these 5 y's, which then leaves me with a y squared inside. And then 3 goes into 13 how many times? 3, 6, 9, 12. And don't be afraid to count on your fingers. So you have a z to the fourth. I could pull out 4 multiples of 3. That gets rid of 12 of my 13 z's, which means I just have a z to the first, or just a z would be the simplified way of writing it inside. Make sure your radical line extends past everything on the inside, or you'll end up getting dinged on a quiz. That is everything from section 5.